You can all see that. So I'm going to talk about performance and scaling of the LFRic model. And so introduce myself, I'm Chris Maynard. I work at both the Met Office and I'm also at the University of Reading. So the abstract for this talk was basically to look at LFRic is the new weather and climate model being developed, and we're going to look at how well that can scale using a new solver that we've implemented, and we use this domain-specific language approach in order to develop the code, and also a little bit about how we're importing the physics prioritizations into the model. So this is reported in 3 papers. There's one last year about LFRic itself, one about the mixed finite element, finite volume semi-implicit discretization for atmospheric dynamics. This is about gung-ho dynamics itself, and then finally there's a paper out this year which is on the performance of the multigrid solver itself. So, okay. So the whole motivation behind doing gung-ho is to transform away from the long lat grid that the unified model uses that we see here with the obvious pole problems into something else whilst maintaining the accuracy of the current model. And so from the dynamics point of view, the principal points about the current grid is it's orthogonal. This is the long lat grid here, quadrilateral and C-grid. Has various good mathematical properties that we'd like to be able to keep if we can, which is the lack of spurious modes, has the good mimetic properties and good dispersion properties. So how can we maintain those mathematical properties when we move to something that looks like this, like for instance the cube sphere? And the way that's being done is to use this mixed finite element approach, the same layout gives the same layout as the current C-grid. Not reliant on the orthogonality condition now, and it gives consistent discretization. So a little bit more on this mixed finite element method. It gives compatibility, which is given by those mathematical expressions we see there. It gives accurate balance and adjustment properties. There's no orthogonality constraints on the mesh, and this does give us the flexibility of choice of mesh. So we could do quads, or we could do triangles, and the accuracy, we could choose different polynomial order. We could choose higher order, for example, if we wanted to. But our target to start with this mixed finite element, and that's what we've implemented so far, is this lower order method on quadrilaterals. And so we have these different spaces that we see that we're given by this expression here, and we then represent those with where on each cell the degrees of freedom live. So we have pointwise scalars, we have circulation vectors, we have flux vectors that go across the face of the cell. These spaces are all continuous in finite element speak, and then we have the volume integrated scalars in W3, which is the pressure and the density, which is represented by the degree of freedom at the cell center. And these are discontinuous spaces, so these have different properties when it comes to doing the computation. And we have pointwise scalars as well for potential temperature. So that was a little bit of the background to the mathematic changes to gung-ho and why we're doing it this way. And the whole point is to get away from the long lat grid and replace it with an unstructured mesh, which should improve the scaling. Having done that, we decided about how we're actually going to write the software. What's the approach for the software? We're taking a domain-specific language approach. And why is that? Well, there are simply too many programming models. Most people seem to think we can probably manage with MPI plus X, where X is probably something like OpenMP or OpenACC, but perhaps you're going to talk to Cocos, perhaps you're going to couple to Intel's One API. So there are a lot of programming models out there, and even if it is MPI plus X, that's still 2 programming models, not 1. There's a rapid evolution of diverse sorts of hardware, and each one of those seems to require a different sort of X for MPI plus X. And so we end up with this parallelization optimization code polluting the science code. And so you mix these things up, and how do you manage your science code when it's full of all these different sorts of code for different sorts of programming models for different architectures? And as we've seen from previous speakers, it's actually really hard to even if you can decorate or annotate your source code with different directives for different architectures, that's probably not enough. You probably need different code structures and loop orders for different architectures. So this is a really problem for how do you maintain single source science code. So we're going to choose this domain-specific language approach, and we do that by restoring the separation of concerns between the mathematics and science code, which is to solve the math problems you want to solve, and the optimization and parallelization code, which is just methods by how we achieve that faster than real time. So we have this layered software architecture to get this separation of concerns back. This is represented by the diagram on the right. So we have, for each single model, we'd have like algorithm code, which is a high-level representation of solving an algorithm. And we have individual kernels, which are the mathematical operations themselves. And in between these, we have the parallelization system, or Sci layer, where all the parallelization and optimization code is going to live. We encode these rules between the layers by using Fortran 2003 object-oriented API, and so the whole thing is embedded in Fortran. So it's a domain-specific embedded language in Fortran. And if we do that, we can then use our Cyclone code, which is a Python application, to parse, transform, and generate the parallel code that we need, using its own intermediate representation of what we're doing. So a little bit about Cyclone. This is an application, it's a Python code that's developed at STFC Hartree by Rupert Ford, Andy Porter, and Sergi Sisso. Please also see Sergi's talk later in the week, Thursday, 8 a.m. If you want to know more about the how Cyclone works itself, because this is just a cartoon or a high-level schematic. There's also people at the Met Office. Eva Kavcic works quite a lot on Cyclone. I dabble. There's some other people as well, and there's also Jörg Heinrichs from the Australian Bureau of Meteorology, who develop in Cyclone itself. So basically, if you have your code, then the Cyclone code has a parser, so it will read the code, and then you can just generate your algorithm, use the algorithm generator to generate the actual algorithm code that you give to the compiler, and the parallelization code that you give to the compiler. But you can also do transformations to change that depending on what kind of parallelization you want to achieve. So that's a very high level schematic or sketch cartoon of what Cyclone actually does. So in terms of LFRic code, how does that work? So this is a couple of screen grabs of some actual LFRic Fortran code. And this is up here is the header for a kernel. It's the header for a kernel, actually for a matrix vector routine. And as you can see, it's just some Fortran. But this allows us to capture the rich domain-specific information for what it is we're actually doing. So that's computer science speak for writing it down, what we're going to do. Because we already know more things about the problem we are encoding than you can directly capture, than you can express in the semantics of Fortran itself, we can actually use that information to help us make choices about parallelism. We're actually going to write it down in Fortran. We could have chosen, for example, to use a special sort of comment or something like you do annotating for OpenMP or OpenACC, but we've decided to embed the whole thing in Fortran, which is what you see here. So these then have some meaning for Cyclone, so it can make reasoning, because it can reason about the horizontal looping and to exploit parallelism based on this information that we're giving it. Kernel itself is just vanilla Fortran. So it's just loops and arrays, and that's pretty much it. So this kernel itself is just y equals mx, where m is this local matrix assembly. The matrix is assembled locally just in a cell, and the horizontal looping is then generated in the Sci layer. So let's look at that as an example. So here's some generated Sci layer code. So by default, Cyclone will just generate serial code, but with distributed memory parallelism switched on. So this is LFRic code. So the first thing we see up the top here is we can see a Cyclone generated something called a built-in, which is a set scalar type operation, and it's done pointwise. So it doesn't have to be a kernel itself. Cyclone can just generate all this in place. So if y is our field here, it's going to loop over all the degrees of freedom up to the last owned DOF and set them all to 0. Okay, having done that, it's then going to go through and look at the data access descriptors we saw in the previous slide, and it says, okay, I'm going to increment y and I'm going to read from x. So I better have both those halos up to date before I do that, so I need to trigger some halo exchanges. Then it knows what looping it's going to do. Okay, so I'm going to loop again, so I'm going to loop all the way to from the cell that I own, all the way to the last halo cell, and then I can call the kernel for that. Afterwards, I have to set the y field, set the halo flag to dirty, because that will need updating if anyone else wants to do it. Anyone else wants to read from that field. So that's basically what the kind of stuff it will generate. It just generates more Fortran. So here we see halo exchange, which is on a field, and that is then part of the LFRic infrastructure code, which then calls something called Yaxt, which basically then calls down to MPI. But we can look at other transformations. So there's something I talked about the degrees of freedom. So here is a shared degree of freedom that belongs to cells that are then partitioned. Okay, so we have partition 1 and partition 2. And here, if we're looking down onto the mesh, this degree of freedom that lives on the edge or the face here is shared by both cells. But this is partitioned. And so cell in the partition 1 is the own degree of freedom, and the cell in partition 2 has a copy of that degree of freedom, has a copy of that information there. So it's called an annexed degree of freedom. So for example, for pointwise computations, for example, to set a field to scalar, you can loop over you need to loop over all the DOFs. If we loop to all the looping over all the own DOFs, then I need to halo exchanges required to get that information correctly set in the second partition, in partition 2. So if I loop just all the owned ones, this gets updated on partition 1, but it won't get updated on partition 2 without a halo exchange. However, I can choose to loop to annexed DOFs all the way to the annexed DOFs, and this is now a transformation in Cyclone. So for a small increase in redundant computation, i.e. both, so this partition will loop and set this value to 0, but so will this one as well, so it is redundant computation, but it dramatically reduces the number of halo exchanges required. So if we do that and we look at the generated code, then we can see there's a bit more code now in the site layer, and we can see what differences we've got. So here now we see with the annex DOF switched on, the first thing we can see is the fact that we redundant compute into the halo. So instead of the loop order going out to the last owned DOF, it now goes out to the last DOF in the halo. Okay, so in this case, this is out to depth 1, and then they're all set to 0. We've also switched on OpenMP, and so it's generated some OpenMP code here, and this is kind of fairly trivial OpenMP, but it does get done in parallel. And so after that, then okay, so now y has been set to a scalar has been set to a 0 before we start. So okay, so let's set all the then it sets all the halo flags to be dirty, but we have computed out to depth 1, so out to depth 1 is now clean. So we no longer need to do the halo exchange. So this leads to a reduction in the number of halo exchanges. That's great. And as I said, we can do it now. Do it with OpenMP. So the other thing you notice is now, because we're also doing OpenMP, is the rest of it we now have to do what we call coloring, because this is for shared degrees of freedom. And you can see that there is some call to the coloring infrastructure up here, and then we use it here. The loop order is now to the last halo cell per color, and then we loop over the number of colors. Then we do OpenMP, and then we do the looping here. So one thing we could think about doing is sharing these two loops in order to make the code go a bit faster, and we could fuse those loops. However, in this case, we can't fuse the loops with this loop with this one, because this Y vector proxy or Y data, the field for Y it has increment data access, and so you would get the wrong answer. And so the fact that we actually write that down in the kernel header means that Cyclone can then make the right choice about what optimizations it can do. So back to Gung Ho then. So the Gung Ho discretization itself, it's inspired by the iterative semi-implicit semi-Lagrangian schemes used in the unified model. Transport uses high order upwind explicit Eulerian finite volume scheme. The wave dynamics use an iterative semi-implicit lowest order mixed finite element method, which is equivalent to the C-grid Charney-Phillips staggering that the UM uses, given by these mathematical expressions here. In terms of computation, the time step is most for the dynamics itself goes basically pretty much goes like this in a loop. So we have this computation of this update, which we then have used to compute the linear operator and evolve the system forwards. So we can compute the slow physics, compute the dynamics forcing, and then we have this double loop. We have an outer loop where we do this twice, and the inner loop itself also runs twice. So we abect the fields, compute the fast physics, then in the inner loop, we compute the dynamics forcing and then solve the linear system, compute the dynamics forcings, solve the linear systems, then advect the fields, compute the fast physics, and go back to the inner loop again. So that's how the time step works. For the linear solver itself, we are using GCR to iteratively solve the mixed system. That typically takes about 10 iterations for each time step. Then from that we form the mixed Schur complement and use that, and then we solve the multigrid Helmholtz system for that and apply the smoother on each level. The error itself is determined by the convergence of the mixed system, and the multigrid V cycle is used to speed up that convergence, and I'll show you how that works in a second. So multigrid itself, so we have the Helmholtz system, is solved using a single geometric multigrid V cycle with a block Jacobi smoother, where the H is given by this expression here. The block Jacobi smoother has a small number of iterations, i.e. 2 on each level, and then we do it in exact tri-diagonal vertical solve, as we only do the multigrid in the horizontal. Solver itself has this structure of having an iterative solver. An iterative solver has an operator and a preconditioner and operates on a vector. So then we can have different solvers, GM-res, conjugate gradient, bicycle stab, etc., different preconditioners, the Schur preconditioner, or multigrid, or something else, and they operate on vectors of fields. So in terms of actually the code, we end up with this nested solver where we do the GCR, and the GCR has an operator which is the Schur preconditioner, and that itself is and has to solve, uses biCG stab and multigrid for the Helmholtz operator. So this allows for an easy implementation of quite a sophisticated nested solver. We can use the multigrid preconditioner to reduce the work for the iterative solver. So it's faster and then uses less global sums, which gives better scaling. So some initial results looking at a cube sphere with 190, a C192 with 30 levels. So C192 means there's 192 by 192 cells on each panel of the cube sphere with 30 levels. That gives us a roughly 50-kilometer resolution. I'm running something called the baroclitic wave test on the Met Office Cray XC40, running on 64 nodes, so that's up to 2,500 cores. It's mixed mode, both MPI and OpenMP, and all that parallel code is generated by Cyclone. And so we can look at different the cost of different solvers or different combinations of solvers. We can do the Krylov subspace solvers for the inner solve, which is biCG stab in this case, or we can look at just doing multigrid only and taking the result of the multigrid preconditioner and treating that as the actual answer, or we can take the multigrid preconditioner and then run Krylov subspace on top of that again, and we can use different numbers of levels, and we can look at different accuracies of the Krylov subspace solve. So you can see they take different amounts of time. So and the fastest being just the multigrid on its own, but multigrid as a precondition to Krylov is faster than just Krylov. However, if you look at the residual, the change in the value of the residual vector for the Krylov solve and compare that to before and after the multigrid, then it looks like multigrid is kind of giving us the equivalent of a solve, Krylov solve for 10 to the minus 2 for a 3-level multigrid solve, which seems to be the most effective for this resolution. So we're going to do the scaling runs and compare the following solvers. So we're going to look at 3 solvers, multigrid 3 levels, with multigrid for the inner solve as a precondition only, with no BiCG stab. So we just take the result of the multigrid preconditioner, and that will be our answer for that inner solve. We'll compare that to 10 to the minus 2 BiCG stab, and we'll compare also that to 10 to the minus 6, much more accurate solve using BiCG stab. We'll look at the scaling for this on a much higher resolution mesh, so a C1152 cube sphere, again with 30 levels. So that gives us about a 9-kilometer resolution. Again, it's the dynamics only, a baroclinic wave test. In order to look at a similar time step that we did before, we're looking at we can compare the acoustic CFL in the horizontal, whereas we were looking at that previous example had a CFL acoustic of about 8. So if we keep it about 8, then that's a time step of about 205 seconds for 400, and we'll look at 400 time steps. So again, running on the Met Office Create XC40, that's again at mixed mode, 6 MPI ranks per node, 6 open MP threads per rank, all parallel code generated with Cyclone. So we can compare running on 384 nodes, that's 13,000 cores, out to 3,500 nodes, that's 124,000 cores. So this shows some quite strong scaling. So we start off with a local volume of 24 by 24 cells, all right, each with 30 levels, and then as we scale out to this one here, we drop down to 16 by 16, 12 by 12, and 8 by 8. So the amount of data per core is getting quite small. So we are pushing into the strong scaling regime here to see how well we really can scale this problem. So let's look at some results. So this is for the whole semi-implicit solver firstly. The bottom panel is the parallel efficiency. So that means 384 is 1 by construction. And then we'll see how well, as we increase the amount of resource available, how well does it scale, and 1 is perfect scaling. So the numbers jump around a little bit. That's because of the network variability of running on such a large cray. It also depends on what else is running in the machine, what network path you take through your MPI jobs. Messages take through the machine, so there is some network variability there, so it does seem to jump around a little bit, but all of them show okay, not brilliant scaling, but they do get out to 3,500 nodes, and the parallel efficiencies drop down to about a half. If we look at the relative cost of the Krylov subspace solvers compared to the multigrid solver, so here higher is better. So at 384 nodes, the multigrid solver is 3.5 times faster than the Krylov subspace solver with solving 10 to the minus 2, and it's about 7 times faster than the Krylov subspace solver with solving 10 to the minus 6. We can see how that scales. This is the same data, so again we see this jump, not smooth data, but it's jumping around a bit. But as you can see, then it looks like multigrid is scaling a bit better because those numbers are a bit higher as we go out to more nodes. But of course, the semi-implicit solver itself is having to do its outer iterations, which do include the global sums for GCR. If we look at the inner solve, the pressure solve, just the pressure solve itself, then here we can see that the multigrid solver, which doesn't have any global sums, is scaling much, much better. So again, we see the data is not smooth, it's jumping around due to this network variability, but the multigrid solver is staying pretty close to 1, even out to 3,500 nodes, where the local volume is very, very small. If you look at the Krylov subspace solvers, their parallel efficiency is dropping off back to down to a half again, because it's having to do all those global sums. If we look at the top panel, we can look at the relative cost of the multigrid solver compared to the Krylov subspace solvers, and it starts at about 4.5 for comparing to solving to 10 to the minus 2, and gets as high as beyond 10 times faster compared to the Krylov subspace solver with a residual set to 10 to minus 2 on 3,500 nodes, but it's compared to the Krylov subspace solver of 10 to the minus 6, it's a whopping almost 25 times faster on the if we just do multigrid only. So we look at the communication costs themselves. Here the upper panel shows the time per time step. So here lower is better. The upper panel shows the local communications. That's the Halo exchanges, how that scales with the number of nodes and thus data size. So you can see that as the local communications are bandwidth bound, as I go use more and more processors, each communication has less data because there's less halo, although that halo is now bigger relatively to the interior. So the ratio of comms to compute gets higher, but as we go into the strong scaling regime, but the actual amount of data per MPI rank does go down. So the actual amount of time doing halo exchanges does go down, but not relative to the amount of compute. If we look at the bottom panel in blue, this is the cost of MPI or reduce, which comes from the global sums, and you can see it's a massive reduction for multigrid. For the multigrid solver, there is no global sums in the inner solve. There are still some in the outer solve, but that's not most of the global sums. That's only a fraction of them. And this is what's really killing the scaling of the Krylov subspace solvers, is having to do all those global sums. We can also look at varying time step. And as you can see, if I make the time step smaller than and so the CFL number goes down, then for the other solvers, the Krylov subspace solvers, they have less work to do, so they go faster. You can see it in the number of iterations, and which is this number's here, and you can see it in the time. However, the multigrid solver is a fixed procedure, so the longer you make the time step, providing it's good enough, the outer solve will still converge. And if we look at that graphically, you can clearly see that here, that as I increase the CFL number, as I increase the time step, the Krylov subspace solvers have to do more work in the inner solve to get that time step to convert, the outer solve to converge, but the multigrid solver, if it's good enough, is good enough, and so it doesn't take any longer. So it's great because it scales really well, it's less expensive, and I can try and should be able to increase the time step. So I'm about to run out of time, so I'm going to just quickly skip to say we're looking at getting the UM physics in. So the UM physical parameterizations are being included. We have a way of doing that in that's not super optimal, but at least gives us the right answer. And then we're looking at how we're speeding that up by changing the data layout and loop order for LFRic. We also just saw Minju's talk, who's looking at how we get the physical parameterizations to run on GPUs. That's relevant for both the and for LFRic. So as we go through, we increase the amount of physical parameterizations we include, we get a more realistic model. I don't really have time to talk about other architectures, but we haven't done as much there as we would like. So in conclusions then, we have lots of improvements to using the domain-specific language optimizations, improvements to formulation, gives us better stability and accuracy, lots of improvements to the solver and a great scanning performance for multigrid, as multigrid is faster and scales better, and we're including the physical prioritizations and looking at the performance for that. Thank you. So I guess I'll look and see if we've got any questions coming up. Yeah, so I've got a question. Matt says, do you foresee a role for mixed precision in your algorithms? Yes, absolutely. So that's one of the pieces of work we're doing this year, is to support mixed precision in LFRic, and the idea being that we would then be able to have different parts of the code running in different precision. And so we definitely look at running the solver in lower precision, 32-bit, and then maybe you might think about trying to do other bits of multigrid on lower precision still, or indeed mapping that to different architectures. And we're also looking at how we would do the physical prioritizations in mixed precision. So one piece of work is to get that working with Cyclone and in the LFRic infrastructure, and that's quite well underway. And then there's looking at the mathematics and combining that with the science for each individual piece. How do we combine those? What's the correct mathematics for working at lower precision for each individual piece? So there's the two pieces to work to that. But yes, absolutely, lower precision is something we are definitely going to try. And then another question, do you think you will have to parallelize in the vertical dimension for your physics packages on accelerators? Yes, I think that's something we will definitely have to do. The previous speaker showed some of that work of how we think we might be able to do it, and we're looking at how we would do that using tools. So we've started with two parameterizations, one Socrates, the radiation, and another one Cassine, which is the macrophysics package. But in general, we'll have to look to how to exploit the vertical dimension, not just for the physics packages, but also for the dynamics if we're running on accelerators as well. So that's something that definitely we need to work on.